All right, hello, and welcome back. And in this video, I'm going to be talking about volume to solid part two using the method of disks and washers. Okay, so this method involves revolving a region around some axis of integration, either a horizontal line or a vertical line. For category one, we will revolve around a horizontal line. So we're going to integrate with a variable, integrated on X. So we're going to suppose we have some region R, which is bounded by F and G between X and A, or sorry, from X equals A and X equals B, so that the vertical line of X is equal to just the absolute value of F minus G. Constant theme that I keep talking about, know the vertical line. And we want to rotate R around this line, Y equals K, some horizontal line. So I showed R up here. It's this yellow region right here. What we're going to do is we're going to revolve it like I show here, and you can kind of visualize it. And here I have our 180 degrees rotated. And if we rotate it completely, we're going to form a new solid, right? And definitely recommend searching out the animation. There's a lot of good animations. Come back once you've kind of visualized it, right? But the whole idea is we're gonna have a hole in the middle and we're gonna have a solid formed on the outside. And this is kind of the cross section right here, what I have at X. Remember, if we want to find the volume, we need to find the area of the cross section. Now, this area is a difference of two circles. It doesn't look like a circle, but if I were rotating it, right, and I faced it the other way, then it would be a perfect circle, right? And I've shown this right here. We have an external radius, an exterior radius, basically, and an interior radius, right? And the area is just pi r squared minus pi r squared for the other one, right? And we can find that, but first we need to find the exterior and interior radius. Now, the interior radius, which we're assuming G is below F, the interior radius is just taking the difference between G and K. Now, of course, what's the difference function? It's the absolute value. So we're going to take the interior radius to be the absolute value of G of X minus K. Same thing for F of X and the exterior radius, right? And now our cross-sectional area at X, X can be anywhere, right? But that cross-sectional area is pi RE squared of X minus pi RI squared of X. We factor out a pi. That's the difference of area of those two disks, all right? That gives us the actual area of the cross-section we're looking for. And here, like I said, I have a cross-section which actually is at the right angle to kind of show you what it might look like. Now, R of I can be zero. R of E, though, has to be positive, right? That's the only thing. R of I can be zero, but R of E definitely has to be a number that's not zero. And the volume by what I just showed you in the last video with slicing is just pi times, because we're going to factor out a pi. We're going to integrate from A to B, right? Accumulate those cross-sectional areas of this. And we're going to factor out sort of a pi to get that this is our volume formula that you absolutely need to know. All right. And if you can't remember it, just derive it, right? Remember kind of you need to know slicing, that you do need to memorize. But once you memorize that, then you know how to get the area. You can get this pretty easily as well. The key here is to find the exterior radius as a function of x and the interior radius as a function of x. Here's an example problem. A bullet, right? The shell of a bullet, I should say, can be modeled by taking the region enclosed by y equals square root of x, y equals x over 10, and x equals 4, and revolving the region about the x-axis. So the bullet can be modeled, right? At least the shell, with some hole in the middle by revolving this specific region about the x-axis. Find the volume of the bullet shell. Now, I have it graphed out for you and I have the hole. Here is what the bullet shell might look like. All right, this is what it looks like. So you can kind of see how it's a bullet. It has a hole in the middle, right, which I showed. It's pretty aerodynamic. Not really. But okay, that's the problem that we're given. And how we might want to go about it is recognizing we're revolving. So we're going to need to use this formula. So I did a 180 revolution to here on the bottom to show you what it looks like there. And I have right here this cross section, right? And we're going to create a cross section anywhere, some arbitrary cross section at some point X. So let's call this X. All right. And we need an exterior radius kind of and an interior radius. All right. So we need those two circles and we need to find the difference in area of those disks. I have this shown right here at an angle, obviously. If I had it at the right angle, it would be a perfect circle. All right, and our exterior radius is the square root of x. Since we're considering the x-axis, that's y equals 0. The exterior radius is just the square root of x, right? Now the interior radius is 1/10 of x, right? We notice it's the line in between the axis of integration and the outer line, right? So that will be on the interior, so it'll be our interior radius. That's 1/10 of x. The absolute value of that minus 0, which is the absolute value of 1/10 of x, which is 1/10 of x. And now it's a straightforward application of the formula. Obviously, we're going from 0 to 4 because it says and x equals 4. So we plug into our formula, we plug it into our calculator maybe, or we solve it by hand. Either way, we should get something around 24.46253. And if not, be sure you can get to that answer, right? And now we're going to move on to category two. And believe it or not, this video is actually pretty short because I'm not going to even go over a problem for category two. I don't think it's necessary. Category two is the exact same thing, except integrating about the y-axis, basically. Essentially, we have that our axis of rotation, right, our axis of revolution now becomes a vertical line. Now we need a function of y and we need a function of g. So like the area, we might have to take inverses. That's the only thing. Definitely look out if you have to take an inverse. Now this line is x equals k. It is not the y-axis. This may be the x-axis, sure, but this line specifically is the line x equals k. All right, keep that in mind. And this is our region, the yellow region here. I rotated it 180 degrees here to show you, and you might want to visualize that. One way to do that is through this right here, sort of. This region might create itself, as you may or may not notice, something like this. It doesn't have to be perfect, but you get the idea kind of how it might revolve. It looks like actually a barrel. Now, a very weird barrel that's very hollow. Like it forms a very hollow region, and the region it forms is a very weird region. But if you actually just take that and revolve it around, then it kind of looks like a barrel. It's only the inside that's kind of weird. And that's interesting, but using the exact same thing that we did before, just with y and just with f of y and g of y, we just have that the interior radius of y is the absolute value of g of y minus k, and the exterior radius of y is the absolute value of f of y minus k. That gives us the volume to be pi times, and remember we're integrating from a to b, so we have pi times the integral from a to b of this difference of squares, dy, all right? Be sure that you have a function of y and it's in respect to y if it is indeed category 2. And in order to differentiate for the disks and washers method, category 1 has a horizontal line that we're revolving around, and category 2 is a vertical line. Like I said, I won't be doing a problem because it's very similar to category one, but as long as you know kind of how to set it up, how to visualize it, and how to get to this cross-sectional circle, and then just obviously taking the difference, eh, this is our key. Once we have this, we just plug it into the formula, honestly. This is the most important step that we can get to, and it's actually so easy, it's not even funny. So if we can get this, then obviously the volume is literally, as you might say, light work. All right. So good luck studying. And in the next video, I will be discussing finding volumes through cylindrical shells, something a bit more interesting, if you want to say.